Okay, great. And I'll also make sure to use this so online people can see it better. Okay, so as I mentioned, I will start first with a brief overview about ALMA, which is the Atacama Large Millimeter and Submillimeter Array. And this is located in Chile. You can see this beautiful image here. And as I mentioned, this workshop, also my ALMA ambassador role is supported by NRAO. So first, please let me spend a few minutes like advertising about NRAO and like let you know what they are doing, and also because they are paying for the lunches and stuff. So okay, so NRAO is National Radio Astronomy Observatory, and they are the headquarters is located in Charlottesville, Virginia, and they are it's actually a building inside the campus of University of Virginia, and they are funded by the National Science Foundation to like operating many radio telescopes. So here you can see, of course, the image on the top is ALMA in Chile, and also there are some well-known telescopes like the Jansky Very Large Array here is located in New Mexico, and it is observing at a longer wavelength than ALMA. And another very famous array they are operating is the Very Long Baseline Array, which you can see here. Basically, they have 10, I think, or 25. I think it's 10 antennas spreading over the globe. So this is because they want to create very long baseline, like which is like very far distance between two antennas, so that we can get a super high resolution image. So I think the longest baseline is from here, on the Mauna Kea in Hawaii to the U.S. Virgin Islands. So this created a baseline of about 8,000 kilometers. So yeah, so NRAO is one observatory, but operating 3 world-class facilities: ALMA, VLA, and VLBA. And in addition to these well-known facilities, other affiliated telescopes, including the Green Bank Observatory. So this is in West Virginia, and I think NRAO operates Green Bank telescopes until 2016, and then it is later, yeah, maybe Michael know better, and then later, like the Green Bank Observatory, like is fully in charge of those telescopes. But I think maybe they are returning back to NRAO pretty soon. This is what I heard.
It's under discussion, it might be possible, but for some time recently, the NSF kind of took away funding from Green Bank down from like most of it to around 30%, but I think now it's going to be increased because they're, you know, the Green Bank has also like demonstrated the utility of having a really nice single dish telescope operating at like really high frequencies too, to discover like many new molecules and do a lot of astrochemistry. So I think maybe they might increase their investments again. Maybe they already have, maybe Mount Blue there, but yeah, for some time it was defested, which was very sad, but it still maintained, so then it became pretty much independent, but they would still like to have NSF funding.
Yeah, that makes sense. Yeah, I heard that like they are at least increasing the percentage like of NRAO of the Green Bank. Yeah, and also NRAO operates some exciting projects, including the next generation VLA. So I'm not I'm not an expert on NGVLA or Green Bank Observatory, but like all the information on their website, and feel free to check it out if you are interested. Okay, so as you may have noticed, all the telescopes I've shown that NRAO operates, all these radio telescopes are ground-based telescopes, and this is because so this is the electromagnetism spectrum that you should be like, I'm sure we all are familiar from our physics class. So the reason why these radio telescopes are all on the ground is because we are observing at the radio wavelengths where the atmospheric transition like allows them to come to penetrate the atmosphere, and then we can observe it on the ground. So it's not like shorter wavelengths like ultraviolet, X-ray, and gamma ray. So in these wavelengths, we have to rely on space telescopes to observe, but like with radio wavelengths, we are able to observe on the ground. And so here you can see that the VLA and ALMA actually spans a continuous spectrum in radio and millimeter wavelengths. So there are actually a synergy between these telescopes. So for example, in terms of studying ISM in nearby galaxies, the VLA is known to be good at observing atomic hydrogen lines. It's at 21 centimeter in wavelength. And we know that atomic hydrogen is mostly distributed on the outskirts of galaxies. And ALMA is known for observing like the molecular gas, which is more in the inner disk of galaxies. And we know they are important in forming stars in galaxies. So like, for example, we can combine VLA and ALMA to study like all the gas phase in galaxies, like how they transfer from atomic hydrogen on the outside to molecular gas on the inside of galaxies. And so there is a wide range of science you can do with NRAO telescopes. So this actually can range from local to distant universe, starting from our solar system to star forming region, exoplanets, and nearby galaxies, and to even larger structure like galaxy groups or clusters, and all the way to cosmology. So the point is just that whatever science you are working on, there is a high chance that ALMA can be helpful in some way. And you don't need to be an expert to propose ALMA observations. Okay, so that's the end of the advertisement for NRAO. Now let's go into our main topic today, which is ALMA. So what is ALMA? ALMA is a 66 antenna array that is located at 5,000 meter elevation in the Chilean Andes. And the whole ALMA project is a global partnership that involves North America, Europe, and East Asia. So there are headquarters actually in all these regions. The headquarters in North America is, of course, NRAO in Charlottesville. And headquarters in Europe is in ESO, the European Southern Observatory in Garhi, I think. And in East Asia, the headquarters is in Japan. It's in NAOJ, but it's also cooperated by AJA in Taiwan and CASI in South Korea. And so, and like if you are in any country outside of these regions, you could always like ask for support from any of these ALMA regional centers. Okay, so as I mentioned, ALMA consists of 66 reconfigurable and high precision antennas. And these 66 antennas include the main array, which has 50 12-meter size antennas. And there is also an ACA array that is more compact and has 12 7-meter size antennas plus 4 12-meter antennas for total power, which is single dish observations. And I'll talk more about why we need this combination in my next talk in radio interferometry. And there is a total of 192 possible antenna locations. So this leads to array configurations expanding from 150 meter to 16.12 kilometer. That is a very large range. So this means the distance of the maximum distance of two antennas in different configuration can range from 150 meter to 16.12 kilometer. And this is very important for reaching a range of resolution and like the largest angular scale structure that I will mention in my next talk. So just an overview, like ALMA is currently the state of the art, and that is not only because of the huge collecting area that has the state of the art sensitivity, but also they have huge number of baselines that allows enough sampling on the frequency space, which is also something I will talk about in my next talk. But all you need to know is that this huge number of baselines can really provide an excellent image fidelity, which is unlike previous radio interferometers on the world, which has limited amount of antennas. And another great thing about ALMA is it has a wide spectral coverage. So here you can see this image is the atmosphere transmission versus the frequency. And the vertical shaded area here are each band covered by ALMA. So it ranged from band 3 here all the way to band 10. And so you can see that all these spectral windows covered by the ALMA bands have at least 50% or more atmospheric transitions. And so it's basically trying to cover as much band as possible, like during this millimeter wavelengths. So as a summary, ALMA can reach very high angular resolution. And so I think the most important point is summarized here, that ALMA is 10 to 30 times more sensitive and has 10 to 30 times better angular resolution than other current millimeter interferometers. So it is the state of the art in angular resolution. So this 0.0048 arcsecond is the highest angular resolution it can reach. And it is so this resolution is based on band 10, which is the highest frequency band, and also the maximum configuration C10, which means the antennas are most widely spread. So that would allow us to have the highest possible angular resolution. And it gives sensitive precision imaging from 35 to 950 gigahertz. So especially I want to mention the lowest frequency band, band 1, just started last year in cycle 10. So that's very exciting. And it's also state of the art in terms of low noise, wideband receivers, high spectral resolution, wide bandwidth, and they also provide full polarizations. And I think the best part of ALMA is it has great science data support. So all the science data are publicly archived and you can access those freely. And they also have some pipeline processing and data reduction support so you can easily process your data with the standard pipeline. Okay, so so the current status of ALMA, the construction of ALMA is already ended in September 2014. And so ALMA has been giving us great science for already more than 10 years. And the routine science observing has been out to greater than 16 kilometer in terms of baseline. So this is the longest C10 baseline, which I'll mention more details later. And as I mentioned, there's 66 antennas. And I want to mention that so some of these antennas will be like constantly in under maintenance, but for every PI science observations, they ensure you that you will at least get a minimum of 43 antennas in the 12-meter array and a minimum of 10 antennas for the 7-meter array. So this number of antenna is guaranteed for science observations. And also a new exciting thing for this coming cycle 11 is that now 9 of the 10 bands are offered in all configurations from C1 to C10. So so this is band 1 to band 10, and band 2 has actually not come out yet. They are still working on it. So basically all the bands at all configurations are possible for this cycle. And so you can always find the latest information on the ALMA Science portal, which is basically just type in almascience.nrao.edu. And so this is a very easy to use website that includes all the documentation, infos, and news about ALMA. And also the NRO also holds many ALMA related workshops, just like this one about ALMA proposal preparation, but also there are workshops on data processing, data reduction, which will happen later in the year, and I will also be organizing another one. So mostly happen in September or October. So if you get ALMA data and not sure about the reduction or data processing, you could also attend one of those workshops, and you can always find the information on this website. And also, NRAO spend a lot of time on documentations because they really want people who are not an expert to be able to also jump right in. So if you are new to ALMA, you can definitely start with this ALMA primer. So this ALMA primer includes some basic introduction to radio interferometry, and also it tells you what kind of science you can do. So it's also on the website I mentioned. So after reading ALMA primer, you could become like the baby Yoda level. And if you want to become Master Yoda, you will need to read the Cycle 11 Proposers Guide, which includes all the information on observing modes, new capabilities, and like how to like accurately set up your experiment and observations. And if you want to become the master of master, there is also ALMA Technical Handbook, which includes all the technical details. And yeah, so honestly, I haven't really read the ALMA Technical Handbook because it's like so complicated with so much details, but just letting you know there's an option. And so another ALMA website other than the Science Portal is this observatory website. So here you can also find many information, including, but this is more like to a broader audience, like including scientists, but also other than scientists. So there are some outreach, multimedia, some news, and also some events they're holding. And you can always find a lot of pretty pictures on this website. So in the last few slides, I want to bring up some science highlights from ALMA. So as you may already know, like one very famous image from ALMA is the HL tau, which is not actually this one, because I want to first show what these protoplanetary disk systems looks like before ALMA. So these are our protoplanetary disks, and before ALMA, we can only see the disk structure, but not really resolving anything within the disk. But after ALMA, you can see very detailed disk substructures in these protoplanetary systems. So this is the famous image. I'm sure many of you already seen that. And just to highlight how high resolution this is. So for example, in this system, the resolution is actually like 1 AU. So it's the distance of the sun and the earth already. So that's a big breakthrough with ALMA. And another science topic that ALMA is great for is like for studying star formation in our local universe. And this is because ALMA is good at detecting multiple molecular lines, including here you're seeing the carbon monoxide emission. So this carbon monoxide is very widely used to probe molecular gas in galaxies. So here is the FANGS ALMA survey. So FANGS stands for Physics at High Angular Resolution in Nearby Galaxies. So they are mapping CO observation at 100 parsec scale, which is the giant molecular cloud scales, and across almost 100 nearby galaxies. So you can see that their sample covered a variety of morphologies, including like the strongly barred galaxy, the grand design spiral galaxy, or some non-barred and flocculent galaxies. And it is really revealing the detailed variations of giant molecular clouds in these galaxies. So here is a compilation of the FANGS galaxies. This is 90 galaxies in total. And yeah, so this really allows us to systematically study like how star formation at small scales are connected to these large scale galaxy structure or environment. And also, ALMA is useful not only in detecting the typical carbon monoxide, but also the CO isotopologues. So this means the molecule version of isotope. So for example, like 13C16O or 12C18O. And here I'm actually sneaking my own work on CO isotopologues in nearby galaxy centers. So you can see these are typical carbon monoxide observation. These are 13CO, these are C18O. So you could imagine the isotope logs are actually very faint compared to the typical carbon monoxide. But like ALMA ALMA is sensitive enough to detect these isotope log emissions in nearby galaxies for the first time. So so you can see that basically all the CO isotope logs are very well detected, and it's also revealing like structures like arm-like structure, like inflowing gas and a compact nucleus, even within this bright center, just this bright center region of galaxies. And finally, I also want to mention that even in the distant universe, ALMA has also opened a new era of cosmological surveys. So for example, this ASPECTS program shown here is the first line deep field. So this means that they are targeting the Hubble Ultra Deep Field. And based on their observation, they have detected 21 candidate line galaxies, including CO emission from galaxies at Z equal 1 to 5 and C2 emissions at even higher redshift. And so this is very important because like these CO or C2 emissions are telling us that there are dense molecular gas in those galaxies. So this really helps us to map the dense gas and star formation history of the universe. Okay, so yeah, this is just a brief interview for about ALMA. And so before I go to the next talk about interferometry, are there any questions? And if people online have questions, maybe can you help me monitor? Like,
Oh, yeah.
I couldn't see them, right?
I didn't see anything in the chat, but
Yeah, sure.
Some basic proposal questions, or I don't know if there's a next on that, but like what's the timeline for proposals, and how long should you expect to work on one?
Okay,
Like,
yeah,
what
so
details should
I'll
be-
definitely show the detailed timeline later, but so the ALMA observing tool and like all the proposal calls are already released last Thursday, and the proposal deadline is April 25th. So yeah, I'll talk more about that later in the later. Yeah. All right, if there's no question, I will switch to my next presentation.